Thank you for the possibility to be here. This is a fantastic place, a fantastic city, and I completely agree with you. It's I wish you one more 100 years of activity here. Okay, so I will talk about work in progress with a group of people, and the work is actually in progress. So this is already some results, but we are not satisfied. So some points will probably we improved in the next future. Let me start with a very short, I promise, very short introduction on Dirac matrices, because probably, I mean, most people are not familiar, but it's just very simple stuff. So the basic idea is this one. I mean, that's why the name of Clifford is involved in this kind of algebras. So the problem was to extract a square root of a quadratic form, and so you want this identity to be true. This cannot be solved with complex numbers, of course. So he invented hypernumbers, which are non-commutative numbers, which satisfy, of course, you want the squares to be 1 and the double product to cancel. Okay? So this is the essence of this kind of algebra. And so in short, this is the main rule that these hypernumbers should satisfy. Okay? So you can, if you have an arbitrary product of a finite number of gammas, you can move them. You change sign each time you swap two of them, and if two of them have the same index, you can collapse into one. So you can simplify any product, and you can reduce any product to a simple product of different gammas, either 1 or gamma. So you check the number. This is 2 to the n possibilities, and this is the dimension of the algebra that you get. Okay, so it's very simple. And this is a Clifford algebra generated by this kind of hypernumbers. Okay, if you have n of them. Okay, and as it happens in mathematics, okay, only 50 years later, Dirac had exactly the same problem. He had this Klein-Gordon equation, which is a good model for particles moving at the speed of light or very high speed, because it's Lorentz invariant. But unfortunately, this is of second order. This is not so easy to mingle with the quantum physics for several reasons. Probably the main one is because it naturally leads to negative probability distributions. So he wanted to extract the square root. He wanted a first order system of equations, which was, well, a first order equation, which was relativistically invariant. And this is, of course, exactly the same problem. But now, okay, you could take a pseudo-differential square root, right? But this is non-local. If you want to do with equations, you go into matrices, and that's a nice solution. You get something which is not commutative, but you solve the problem. And, bear in mind that here I write n plus 1, because if the dimension is n, you still want an additional mass term, so you have to solve it. You have to find n plus 1 matrices which satisfy the anti-commutation relations. Okay, so this is the summary of what you can do. You can solve the problem in any dimension. The minimal size of matrices that you need is given by this number, which has a step 2. So it's the same number for n equals 0, and n equal 1, n equal 2, and so on. Okay. You can solve the problem with complex matrices in any dimension, and for some cases, modulo 8, you can solve also with the real matrices with real entries, but the size increases with dimension, of course. And of course, the problem is not unique. For instance, in dimension 3, you get 16 different Dirac matrices that can solve the problem, but you have to pick a group of matrices, okay? So to see in concrete, in dimension 1 or 2, so the size, the minimal size is 2. I say minimal because if you have matrices of bigger size, you can also use for lower dimensional problem, of course, because they satisfy the anti-commutation relation, but it's not economical, right? So the minimal size is 2. And actually, this was found before Dirac, 1 year before Dirac by Pauli. So this is a set of 3 anti-commuting matrices. You can use it for dimension 1 and for dimension 2. And for dimension 1, you can pick sigma 1 and sigma 3, which are real valued according to the general theory. For dimension 2, you need all three of them, so you have to run into complex matrices. Okay? This is the standard, one of the standard choices for dimension 3 of space. So these are the 4 matrices. And you can see nicely, you have to go into size 4 to solve the problem in dimension 3 or 4. And you see it's quite clear that you can compose higher dimensional Dirac matrices using block matrices made with the smaller dimensional. So it's clear that there is some nice algebraic structure that you can exploit to construct these matrices. But I mean, this is not the main point here, of course. And I'm not going into geometry, but for some reason which is not completely clear for me, this is also important in Riemannian geometry. So you can, I mean, the same kind of problem can be solved for vector bundles, and you get interesting operators also in curved background. But I will stick to Euclidean case, of course. Okay, so now you compose the Dirac matrices or Pauli matrices with the derivatives, and you get this kind of massive, I call massive Dirac operator if there is a mass, which will be strictly positive here. And when m is equal 0, you get the so-called massless Dirac operator, okay? The spectrum of dm has a gap, and it is not bounded from below, unfortunately. And so you can sum up the anti-commutation relation by saying that if you take the square of the Dirac operator, you get a diagonal operator made of Laplacians or of Laplacians plus m squared, okay? Okay, this is the situation. And of course, when you put the time, you get, when you consider the group, the continuous group in L2, because it's a self-adjoint operator, you get this kind of equation, which can be nicely solved. You have Dirac flow, massive or massless Dirac flow. And of course, I mean, this hides a little the structure. If you write down explicitly, you get, of course, a simple explicit system of equations. So for instance, this is the case of dimension 2, which will be studied here in this talk. So you can see it's very explicit, but okay, we shall say something more later. Okay, again on the spectrum, this is the main annoying feature of Dirac. There is no bound from below on the energy, the spectrum. Here we will consider only the massless case. In that case, the spectrum is the entire real line. And as you can imagine, this gives a lot of problems. This is partially true in the sense that if you use projectors, which are non-local, of course, then you can project the space, the L2, by the way, the elements of L2 to power n are called the spinors, okay? So you can project the spinor space into eigenspaces which are made only of positive or negative energy. But, I mean, this is useful in some cases, but most of the time it is inconvenient, okay? And you cannot really, especially, okay, you can, this easy for linear case, but as soon as you have nonlinearities, this is not so easy to work with. And the constant theme in Dirac equation is this mixture of algebraic properties and analytic properties, which sometimes helpful, sometimes it's a nuisance, okay? Okay, so the basic way to handle Dirac equations is to square them, of course. If you square them, you reduce to diagonal system of nice equations, okay? So wave or Klein-Gordon equations, but you at the same time, you destroy the algebraic structure. And for instance, I mean, the main point in, when we did some results on Maxwell Dirac, the main point was really to preserve the algebraic structure. I mean, some years ago, we proved some almost optimal local existence results and almost critical spaces for Maxwell Dirac and for Dirac-Klein-Gordon. And the main idea was that, I mean, people before us were taking the square, and if you stop taking the square and you preserve the algebraic structure, you can really find the null structure of the system, okay? Anyway, so the main idea is squaring is good, but for finer properties, you don't square. It's better not to square, okay, to preserve the algebraic structure. And we'll see this again in today's lecture. Okay, so if you only consider the constant coefficient case, everything is already known, okay? Because you take the square, you get a wave equation or Klein-Gordon equation. You can really explicitly write down the flow in terms of, okay, this is a diagonal operator wave flow, okay? So for this, you have virtually everything, okay? You can represent the solution, and you can, for instance, you have a full set of Strichartz estimates or Strichartz-Sobolev estimate. I don't dwell into, I hope this is well known, of course. And similar results for the massive flow when you have the corresponding Strichartz estimate for Klein-Gordon. Okay, so this is immediate. And okay, already for the nonlinear Dirac equation, this is just a quick synopsis of what is some of the results. It's not a complete picture, but I mean, just to get some ideas. It is very natural to consider this equation, but let me say up front, there is no result for large data, okay, available yet. Because, of course, the fact that, I'm talking about dimension 2 or larger, okay? Dimension 1, of course, it's typically easier, but dimension 2 or larger, there is no result for large data because of the problem is that the energy is not positive, okay? So you don't have any control. So for instance, the natural scale, the natural problem is in the scale of Sobolev spaces, and there are some early results. There is a first comprehensive result in dimension 3. There is a standard way to find the critical value of the index S, and above S you have well-posedness, local, at least local well-posedness or global well-posedness with small data. Below you have ill-posedness and so on, the standard facts. And this is for dimension 3, but there are corresponding results by a Japanese group for any dimension, okay? So this is more or less what you expect. For instance, already the problem of a global well-posedness in 3D for the cubic equation with in energy space in H1 was hard to solve, okay? Small data, we're talking about small data. Let me mention that you don't have radial solutions. I mean, if you take radial initial data, the solution is not radial, okay? Because of the algebraic structure. And so there is no natural simple case, in simple radial case. But this was a nice idea by Machihara, Nakamura, Nakashi, and Ozawa. You can really nicely exploit Strichartz estimate with the angular regularity for the wave equation, you know well, and which, of course, become sharp if the data are radial. So angular regularity is for free for radial data. So this is the way to handle radial data. But anyway, this was the best result until Bejenaro-Herr and Bourneval-Scandy solved the problem. So now it is known that for small H1 data, the cubic Dirac equation has global solutions, okay? Okay, so, I mean, this is just to give you an impression of most of what you can imagine is true, but there is this big difficulty that you don't have a positive energy. Okay, let me mention something about potentials. How do potentials enter in this picture? Okay, quantum electrodynamics is essentially the theory of Maxwell-Dirac. You have to couple Maxwell, I mean, the electromagnetic field with the Dirac field, okay? Interaction of the particle with a field, electromagnetic field, and the way the prescription to interact is through the vector potential. So you have a field which is described by a vector potential, and you modify the derivative in Dirac by adding this four terms, vector potential. So you have a modified Dirac operator, which is like this, with mass, the mass term is as usual, m beta. So with this prescription, you get the full Maxwell-Dirac system or some simplified versions, which is Dirac-Gordon, and I mean, just mention that we studied this a few years ago, but I don't want to deal with it. So this leads to the main question in this talk. What can we say if you add a linear potential to the Dirac equation? So it's a natural problem. It's important for the general theory of quantum electrodynamics. Of course, you see that the natural potential should be something like that. So a combination of Dirac matrices, scalar coefficients and Dirac matrices. This is what is in the prescription. But of course, a mathematical interesting problem is also generic 4x4, maybe self-adjoint Hermitian matrix, depending on X, or ideally of X and T. You can simplify a little by choosing appropriate gauges, at least if smoothness allows you. So you can, for instance, take out A0. But let me tell you that the situation, the knowledge about dispersive properties of the Dirac equation with potential is a mess. So it's also, this is partially true also for Schrödinger, but there are many more results, of course. So, it's a much older problem. But it's really not clear, the situation. Just to mention one fact, for Schrödinger, you can go very close to critical potentials, and you have some results for critical potentials. Critical in the sense of scaling, and which reflects into the fact that dispersive properties start to fail when you get too close to the critical case of potential. But for Dirac, we are very far from the critical case, okay? So there's a big gap. Anyway, so this is just a maybe complete list of what is known. So several years ago, we proved some pointwise decay in the 3D case for some small potentials, okay, small potentials. This was improved here, some Strichartz estimates or estimates with angular regularity. We tried to improve, again, for small potentials, we got Strichartz estimates. Okay, this is one case of large potentials. Maybe I should mention this is a fun result an old result by Bachelot. You can construct consider the Dirac equation with some special nonlinearity, which is actually what is interesting for physicists. And for that physical Dirac equation, you can construct some very strange solutions, which are actually linear. So on these solutions, the nonlinear term vanishes because of the algebraic structure, okay? And these are large solutions, of course. And Bachelot perturbed them, and this is the only result for which you have global large solutions for a Dirac system, okay? To my knowledge. Anyway, so by exploiting this idea, you can construct some large potential with the special structures for which you have Strichartz estimates. And there is a recent group of results by Erdogan and his group of collaborators, not exactly dispersive estimate, but weighted dispersive estimates can be proved. Even in dimension 1, you have dispersion if you put some weights. Anyway, so I'm claiming here that the critical decay is 1 over x for the potential, but this is not substantiated by the dispersive results. We're very far from proving decay for potentials like x1 plus epsilon or something, okay? But this should be the critical decay. And let me tell you something about this case. So we focus on, this is the main problem I consider here, we considered, 2D massless Dirac operator with a really critical potential, okay? So now A is exactly 1 over x, apart from this. So there is some structure, of course. The scaling is exactly the same as D, so this is critical both from the point of view of decay and from the point of view of the singularity. And so in some sense, this should give some hint at what's going on at the critical case, okay? So, I repeat, this is not substantiated by existing results, but this should be the most critical case. Okay, so what can we say? Okay, there is also one partial justification to study this potential because it's interesting from a physical point of view, okay? So this is the representation of well-known, I mean, the mathematical model for a well-known experiment where you have this wire in 3D, but this is an infinite wire, so this is you use a 2D model to describe it. There is current going through the wire, and then you observe the diffraction pattern of a beam of electrons going through the wire, and after the wire there is the double slit. And you see that if there is no current, there is a diffraction pattern. If you switch the current on, the pattern changes. Okay, so clearly the current, the field, has some influence on these electrons, but it should have no influence because the magnetic field associated with this is zero. Okay, as mathematicians we say this is not zero. If you compute the rotor of this, you get a delta at zero, right? But it is zero in the points where the electron move. So mathematically, it is clear that you cannot say this is zero, but from a physical point of view, this is considered a puzzle. So it's nice to say something mathematically about this problem, okay? Okay. So first idea, take the square, right? If you take the square, you have to say something about what's precisely going on at zero. If you take the square of this operator, of course you get a diagonal operator, but you get some strong singularity. Okay, what do you do with the singularity? You have to understand the spectral theory. Let me tell you that if you consider this is not really the squared operator, it's the squared minus the delta. Okay. And so exactly the same A1 and A2. This is called the Aharonov Bohm Schrödinger Hamiltonian. This one is nice because, of course, it is bounded from below. You have the Friedrichs extension, which is nice, and you can prove a dispersive estimate for this operator. So it works nicely. You can consider both Schrödinger and wave equation associated with this operator. It works. There are some results I mentioned here. So this is a nice operator. Of course, let me mention, this is not the only self-adjoint extension of this operator, okay? You have a family of self-adjoint extensions, but this is the nicest one, clearly the nicest one, no singularity, and it works, okay? So can we think that we just take the square of Dirac and we get this operator and everything is solved? Okay, but you cannot. I mean, apparently it's much harder to study the Dirac equation with the Aharonov Bohm potential. I just mentioned this very partial result, so you get some smoothing estimates, L2 estimates with weights, but I mean, I say something, the results we mentioned here are better. Okay, so let us try to take the square of the A, and what you get really is the Schrödinger Hamiltonian plus a very singular part, right, delta. And so this is a self-adjoint operator. Its square certainly is a self-adjoint operator. H is a self-adjoint operator, so H should be related with this. So why is this delta appearing? So what's going on here? Okay, so we analyze in detail the spectral properties of the A. Okay, this is the space. I mean the correct decomposition into spherical harmonics. So each of these spaces, this is the angular part, has this structure. It's a one-dimensional space. So any spinor, L2, is decomposed into, so the first component this is the spherical decomposition of the first component, and this is the spherical decomposition of the corresponding second component. Let me just introduce the projection on the space with kappa equals 0 and the remaining part, okay, just to handle separately the two parts, because the trouble comes from the component kappa equals 0. Okay, so when you write down into this decomposition the operator, you get so identity in the angular part and some radial operators in R. I write d sigma to mean partial sigma to mean radial derivative plus sigma over R. And so this is explicitly the action of dA, okay? So you see the two components are switched and I mean, theta remains unchanged. And okay, this is the way to write it for smooth functions, of course. Now let us consider this is the description of all possible self-adjoint extensions, okay? This is an exercise, you apply von Neumann theory. And so let me define this subspace of smooth spinors, absolutely continuous, continuous at 0, the value is 0 at 0, and you have some limited smoothness. And all self-adjoints extension of dA form a one-parameter family with the parameter gamma. You can restrict between 0 and 2 pi, it's periodic. And so the domain is made, this is a description of the domain. You have the spinor, the smooth spinors, as before, and one singular component. This is just a constant, and multiples of this explicit function. This is the standard Bessel function, modified Bessel function, second type, some Macdonald function, okay? K alpha is the one that decays exponentially at infinity, and this is always singular at 0. Singularity is of order z to the minus mu. Okay, and so this is the domain, and the action of D, of the self-adjoint extension with the parameter gamma is very explicit, okay? The usual one on the smooth part, and this action here, so you see the two parameters here are exchanged. So this is a complete description of the self-adjoint extensions. Now, what happens if we square it? Well, it's quite clear what happens. I mean, you want, what is the definition of the domain of the squared operator? You want a function in the domain such that after you apply D, this is also in the domain, right? So this is fine, but the singular part, you cannot have this and this, right? You can, the vector cannot be a combination of this and also like this. The only possibility is that this is 0. So when you take the square, just the singular part disappears. You always get the Friedrichs extension of the Schrödinger Hamiltonian. I mean, there is no puzzle. Simply, taking the square destroys the most interesting part of the operator. That's it. So, I mean, this is the explicit computation. It's quite elementary. So, by the way, this is confirmed by, I mean, the full set of self-adjoint extensions of the Schrödinger operator were studied by Damien Tate in '98, and so this is confirmed. We do not get singular extensions when you take the square. We only get a Friedrich extension. So basically, this forces us to work with the full system. We cannot take the square to study the dispersive properties of Dirac. Okay. Okay. So let me tell you what can be proved by working directly on the original operator. Okay, this is partly unsatisfying because once we understood the full set of self-adjoint extensions, of course, we are curious what happens for all gammas, but we are authorized by the standard procedure. I mean, everybody in this field picks the best extension. And so this is our choice of the distinguished extension, the one with the best dispersive properties. So if alpha, oh, by the way, let me tell you that if alpha is larger than is not in the interval 0, 1, you get operators which are unitarily equivalent to the one for alpha between 0 and 1. So we can safely restrict alpha between 0 and 1. And of course, alpha 0 is the standard free operator. So for alpha between 0 and 1/2, we pick gamma 0. For alpha larger, we pick gamma pi over 2. And so this is a standard Pauli-Little decomposition. I'm introducing notation for the following statement, okay? And this is a weight. Notice that the weight is asymmetric in the first component, in the second component. So it's effective only near 0. Okay, so the first result is a pointwise estimate for the flow, okay? For the non-singular part, we get exactly the standard dispersive estimate. These are the same powers that for the wave equation, okay? It's written in frequencies, so decomposing frequencies, but I mean, it's a standard Besov type estimate, pointwise estimate for the wave equation. But for the 0 component, we get a weighted estimate. This is not too surprising. I mean, even for the free Dirac equation, the best estimates are have some weights, so I mean, as a first result, we are pretty satisfied. So the singular component has, we need some weight. And of course, immediately you ask about Strichartz estimates. And okay, we have, so it is natural to develop some theory of adapted Sobolev spaces, which afterwards, you can pose the question if this is equivalent to standard Sobolev spaces, but for the moment, it's fine. We have it is natural to define these spaces using several equivalent ways, of course. And so for the non-singular part, for the components which are not a 0 component, we have the standard Strichartz inequalities. Okay, non-endpoint Strichartz estimates. So for the singular component, kappa equals 0, again, we get a weighted Strichartz estimates. Okay, this is the precise statement, and the weight is like this. Okay. So I think it's not necessary to dwell into the details of this estimate because it's just a standard Strichartz estimate with some weight effective near 0. And let me tell you that for a restricted range of indices, we can get a standard Strichartz estimate without weights. And we are still working on this because probably this restriction can be removed. But anyway, so what this result says is that standard Strichartz estimates hold. So this is really the standard set of indices, provided Q is restricted to a strip, which depends on the parameter alpha. And actually, this bound is necessary. So we have counterexamples for Q larger than Q larger than Q alpha. This one is probably not necessary; can probably be removed. So let me just. So this is the smaller triangle is the standard set of Strichartz indices. The larger one is the standard set of Strichartz indices for radial wave equation. And so for the component kappa equals 0 is a radial component, right? It's just one component. So you have a larger set of indices. And this strip, red strip here, is the one for which we have the intersection of this with the darker triangle is the region where we have a standard Strichartz estimate for the full system. Okay. Okay, so maybe I can tell you something about some ideas of the proof. I mean, it's a very concrete proof because it's a very specific operator, right? But still, you have some work to do. To represent the solution, you have to diagonalize the system. And the idea is to introduce this, system 2x2 version of a Hankel transform, okay? The standard Hankel transform is this one. Okay, there are several definitions, but this one is perfect for us. And this is a very nice theory for nu larger than -1/2. Actually, if I'm not mistaken, this is a unitary operator, which square is, I mean, this is true for nu strictly larger than -1, but this is not written anywhere, but please check. We only use the -1/2, but this should be true for up to excluding -1. Okay, anyway, so this is a standard Hankel transform. F is a spinor. I denote by F1, F2 its components. And we define unitary maps from the set of spinors to L2 of the real line, with also with weight R. This is the full definition. Okay. I mean, this is not out of the hat. This is just a combination with the eigenfunctions of the operator. Okay, it's a standard way to find out what diagonalizes your operator, of course. And we need two different definitions for positive index, for negative index, and for kappa equals 0, we use this one for alpha, I repeat the choice, the special choice of gamma, depending on alpha. And so for alpha below 1/2, this is the definition. For alpha larger than 1/2, this is the definition. For alpha equal 1/2, both are good, of course. So with this operator, so this is the original decomposition of the Dirac operator, we get a perfect diagonalization of the operator. Okay? So this is the natural tool to write, to represent the solution. Once you do this, the flow, so each component of the flow takes this form. It becomes diagonal. And we are reduced to investigate this kind of operators, which are quite nice. I mean, we have a lot of information, explicit information, because of the Bessel function, of course. And so for the non-singular part, we are used to estimate this. And the trick is, we can rely on what we are able to do for the Schrödinger Hamiltonian. But, and this works for all components but the singular one, of course. So if you replace the singular part, which means kappa equals 0, by this, so only positive indices here, you see, then you get the wave flow of the standard Hamiltonian, okay? And for this, I mean, there are some ideas already, of course, by modifying what Zhiqing and Taylor did. It's, I mean, relatively standard to work out the dispersive properties of the Schrödinger operator associated to this. To go from Schrödinger to wave, nice trick is to use a subordination formula. Okay, you can, this works also on, I mean, for operators, of course. You can represent exponential of lambda using exponential of lambda squared, and the loss is exactly the loss when going from Schrödinger to wave. So it's quite nice. And I mean, this trick gives you quite rapidly the properties you need, but still there is some, I mean, you have to develop some, I mean, heat kernel estimates and Pauli-Littlewood estimates associated to the operator to be able to handle the frequency estimates, okay? Okay, so the Strichartz estimates are, as usual, as you can imagine. It's, I mean, a long exercise in some sense, but still there is some work to do to handle the inequalities, okay? And the singular part is the more interesting part. So essentially, you are reduced to estimate an operator of this form with some singularity now. And okay, this can be done by a careful analysis of, I mean, you need some more refined information about Bessel, but not too refined, just asymptotic expansion. And then the proof goes as you expect, Minkowski and Schwartz, and but you still have to be careful when you analyze this kind of operator. Okay, I think maybe I can stop here. Thank you for your attention.